Imagine two particles, as tiny as you can imagine, linked together in a mysterious way. These particles are not just any ordinary particles, they are subatomic, existing in the quantum realm where the rules of classical physics no longer apply. They are connected by an invisible thread, a shimmering line that defies the vastness of space. Even if we separate these particles by vast distances, miles, light years, or even across the universe, they remain connected. This connection is not weakened by distance. It is as if the particles are communicating instantaneously, no matter how far apart they are. Imagine one particle on Earth and its twin on the other side of the Milky Way galaxy, yet they still share a bond that transcends space. This connection, known as quantum entanglement, is one of the most bizarre and fascinating phenomena in the realm of quantum mechanics. It challenges our understanding of reality and forces us to rethink the very nature of existence. Quantum entanglement suggests that the universe is far more interconnected than we ever imagined, with particles influencing each other instantaneously across vast distances. It seems to defy our everyday intuition about how the world works. In our daily lives, we are accustomed to objects behaving in predictable ways, governed by the laws of classical physics. However, in the quantum world, particles can act in ways that seem impossible, defying our expectations and challenging our understanding of the natural world. This essay will delve into the world of quantum entanglement, exploring its history, its implications, and its potential to revolutionize our understanding of the universe. We will journey through the discoveries of pioneering scientists who first uncovered this phenomenon, examine the theoretical frameworks that explain it, and consider the profound implications it has for technology and our comprehension of reality itself. Join us as we unravel the enigma of quantum entanglement and uncover the secrets of the quantum world. Why are there not more people talking about quantum entanglement? To understand quantum entanglement, we must first take a peek into the strange and fascinating world of quantum mechanics. This field of science delves into the behavior of the tiniest particles in the universe, particles that defy our everyday experiences and challenge our understanding of reality. In the early 20th century, physicists discovered that the laws governing the microscopic world were vastly different from those we observe in our daily lives. These groundbreaking discoveries were made by brilliant minds such as Albert Einstein, Niels Bohr, and Werner Heisenberg, who laid the foundation for what we now call quantum mechanics. In the quantum realm, particles like electrons and photons can behave both as waves and particles, a concept known as wave-particle duality. This means that under certain conditions, particles can exhibit properties of waves, spreading out and interfering with each other, while under other conditions, they can behave like discrete particles with specific locations and momenta. This duality challenges our classical understanding of objects as having definite properties and existing in specific locations. In classical physics, an object is either here or there, but in the quantum world, particles can exist in a superposition of states, being in multiple places at once until measured. This phenomenon is beautifully illustrated by the famous double-slit experiment, where particles create an interference pattern, revealing their wave-like nature. Now, let's dive into an example of quantum entanglement. Imagine two particles that are entangled. When one particle is measured and found to be in a particular state, the other particle, no matter how far apart, will instantly be in the corresponding state. This phenomenon has been confirmed through numerous experiments, defying classical physics and showcasing the mysterious nature of quantum mechanics. Today, the principles of quantum mechanics are not just theoretical curiosities, but are being harnessed for practical applications. Quantum computing, quantum cryptography, and quantum teleportation are just a few of the cutting-edge technologies that are emerging from our understanding of the quantum world. These advancements hold the potential to revolutionize fields such as computing, communication, and even our fundamental understanding of the universe. As we continue to explore and unravel the mysteries of quantum mechanics, we are not only expanding our scientific knowledge, but also reshaping our worldview. The quantum realm invites us to question the very nature of reality and to embrace the wonders of the universe in ways we never thought possible. Quantum entanglement takes this strangeness a step further. It's one of the most fascinating and perplexing phenomena in the realm of quantum physics. This concept challenges our classical understanding of the universe and opens up a world of possibilities that seem almost magical. It tells us that two particles can become linked or entangled in such a way that their fates are intertwined. This means that the state of one particle is directly connected to the state of another, no matter the distance between them. This connection is instantaneous and defies the conventional limits of space and time. Imagine flipping two coins. You might expect a 50-50 chance of getting heads or tails for each coin. In the classical world, each coin flip is an independent event with no influence on the other. However, with entangled particles, it's as if the coins are connected. This connection is not just a metaphorical link, but a real physical phenomenon that can be measured and observed. If one coin lands on heads, the other instantly knows to land on tails, no matter how far apart they are. This instantaneous connection, which Einstein famously referred to as spooky action at a distance, suggests that information is being shared between the particles faster than the speed of light. This defies our traditional understanding of physics and has profound implications for the future of technology, including quantum computing and secure communication. This connection isn't a physical link, like a string tying the particles together. Instead, it's a correlation embedded within their very existence. When we measure the state of one entangled particle, we instantly know the state of the other, even if they're light years apart. This spooky action at a distance, as Einstein famously called it, seems to violate the principle of locality, which states that objects can only be influenced by their immediate surroundings. Section 5. Einstein's doubts and the EPR paradox. Einstein, along with physicists Boris Podolsky and Nathan Rosen, was deeply troubled by this implication of quantum entanglement. In 1935, they published a paper outlining what became known as the EPR paradox. They argued that quantum mechanics, while successful in its predictions, was incomplete. They believed there must be some hidden variables yet to be discovered that could explain this seemingly instantaneous communication between entangled particles. Section 6. Bell's theorem, putting entanglement to the test. In 1964, physicist John Bell devised a way to experimentally test the validity of Einstein's hidden variable theory. Bell's theorem showed that if quantum mechanics was incomplete and hidden variables existed, then the results of certain experiments would fall within specific limits. However, if entanglement was truly a fundamental aspect of reality, these limits could be violated. Section 7. Experiments, confirming entanglement. In the decades that followed, numerous experiments were conducted to test Bell's theorem. These experiments consistently showed that the predictions of quantum mechanics were correct, and the limits set by Bell's theorem were violated. Entanglement was real, and the spooky action at a distance that Einstein had found so unsettling was an undeniable aspect of the quantum world. Section 8. Quantum entanglement in action, teleportation and beyond. Quantum entanglement isn't just a theoretical curiosity, it has profound implications for various fields. One of the most exciting applications is quantum teleportation. Despite its name, quantum teleportation doesn't involve beaming objects or people across space. Instead, it utilizes entanglement to transfer quantum information, the state of a particle, from one location to another, without physically moving the particle itself. Section 9. The future of quantum entanglement. Beyond teleportation, quantum entanglement holds promise for revolutionizing computing, cryptography, and communication. Quantum computers, which harness the power of entanglement, have the potential to solve problems that are intractable for classical computers. Quantum cryptography offers unprecedented security for transmitting sensitive information. Section 10. Conclusion. The entangled universe. Quantum entanglement, once a perplexing concept confined to theoretical physics, has emerged as a tangible reality with the potential to reshape our technological landscape. It reveals a universe more interconnected and stranger than we could have imagined. challenging our classical intuitions and opening up new frontiers in our understanding of the fundamental nature of reality. Section 11. Fun fact. Did you know that the first successful experimental demonstration of quantum entanglement occurred in 1982 with photons? This groundbreaking experiment, conducted by Albert Einstein and his team, paved the way for further research and solidified entanglement's place as a cornerstone of quantum mechanics.